We're on our last FRQ topic, topic 10, and this topic is on series. There is always a series question, and it's always number 6 on the FRQ section of the BC exam. So expect this to be number 6. So we're going to begin today. This was our most recent unit that we did. This was our unit 12. So we're going to jump right in to an FRQ from 2018. Number 6, no calculator. So these will always be number 6, always be no calculator. In this problem, they give us that the Maclaurin series for ln of 1 plus x is given by this. So it's a Maclaurin series, so it's centered at 0, which we can see by all of the x squared, x cubed, x to the fourth. There's no x minus some other number other than 0. So Maclaurin series, remember, that is centered at 0. So they give us this Maclaurin series, and they say on its interval of convergence, this series converges to natural log of 1 plus x. That's what a series does. For whatever the interval of convergence, the series is equal to this function. Now it says let f be the function defined by this, x times ln of x plus 1 plus x over 3. So see the similarities here. Part A, write the first 4 non-zero terms and the general term of the Maclaurin series for f. Well, as x goes to 0, this series, ln of 1 plus x over 3, is very similar to ln of 1 plus x. So I would say that f of x is approximately equal to x times ln. So I'm going to be replacing x in this series with x over 3 for this. I'm going to do this in 2 steps. So I'm going to leave this x outside first, and then I'm going to multiply in by that x. So I'm replacing x with x over 3 because that's the substitution that we are called upon to make. So I'm replacing x with x over 3 minus, this would be x squared over 3 squared times that 2. This would be x cubed over 3 cubed times that 3, x to the 4th over 3 to the 4th times that 4, plus dot dot dot, plus negative 1 to the n plus 1. I'm just copying this down. X to the n over 3 to the n times n, plus dot dot dot. So I copy exactly what I see there, except in place of every n, in place of every x, I put x over 3. Now I'm going to go in and multiply through by this x. So we'll have x squared over 3 minus x cubed over 3 squared times 2, etc. And I'm just copying it down. Remember, when we're doing these series, the most common mistake I see is not the kids don't know what they're doing, just a typo, just a right-o. X to the n plus 1 over 3 to the n times n. So that's our first 4 non-zero and the general term for the Maclaurin series for f. This was worth, back in 2018, this was worth 2 points. 1 point for the first 4 terms, and 1 point for the general term. Part B, determine the interval of convergence for f, for the series for f. So I know when I see determine the interval of convergence, I know that means big points for me. These are always worth a lot of points. This time it was worth 5 points. So I'm going to use the ratio test because that's what AP expects us to see. They expect to see the ratio test, so I'm going to give them what they expect here. So I'm using my general term for f. I can ignore the negative 1 since we have an absolute value in the ratio test. I'm going to write the n plus 1 term, so this will be x to the n plus 2 over 3 to the n plus 1 times n plus 1. Now in the ratio test we make a ratio, so we're dividing it by the nth term, which is the same as multiplying by the reciprocal of the nth term. So hopefully it hasn't been so long that you haven't forgotten this. It was our most recent unit. If you've forgotten that step, go back to the notes and refresh yourself on those notes. Now we clean up. So x to the n plus 2 divided by x to the n plus 1 leaves an x in the numerator. 3 to the n divided by 3 to the n plus 1 leaves a 3 in the denominator. These n's do not divide out. We just keep them, and we let the limit take care of them. So as n goes to infinity, n over n plus 1 goes to 1. And we are left with the absolute value of x divided by the absolute value of 3. And we want this to converge per the ratio test. This converges when that limit is less than 1, which means the absolute value of x is less than 3. So x is between negative 3 and 3. That is the interior of the ratio of the interior of the interval of convergence. Okay? We need to test each endpoint. So I'm testing negative 3 and 3. If I put 3 in for x, I will have the sum of negative 1 to the n plus 1, negative 3 to the n plus 1, over 3 to the n times n, which is negative 1 to the n plus 1. I'm breaking apart this negative 3 to the n plus 1. That'll be negative 1 to the n plus 1 times 3 to the n plus 1. Like that. Now, negative 1 is the same base, so I can write these as the same base, and I add the exponents. So that will be 2n plus 2. The 3's reduce to leaves just a 3 on top. Now this 3 is not going to affect the convergence or divergence because of the series, because there's no n associated with it. It's not a 3 to the n, it's just a 3. We could, in fact, take it outside of the sigma, right? Now, I examine this because I need to determine if this is alternating or not. Since there's just an n in the bottom, this is either going to converge or diverge depending on if we're alternating or not. So I notice that I have a 2n, which will always be even. 2n makes just this part always even. And then I'm adding 2 to an always even number, so I'm going to stay even in my exponent. No matter what n is, I'm staying even. So this is always positive 1. So this will be just 3 over n, which is our diverging harmonic, or you can say a diverging p-series, either one. Okay, so it diverges, so we're not going to include x equals negative 3. Now we test x equals 3. We'll have negative 1 to the n plus 1, and I'm replacing x with 3. If we clean that up, the 3's reduce and leaves just a 3 on top. So again, this is alternating. This series will be alternating. So we're alternating with 3 over n. That is going to be our converging alternating series. It converges by alternating series test. Or you can say a converging harmonic series, because that's what we have here. So the interval of convergence is negative 3, not including the negative 3, but including 3. So this is exactly what you need to show them. Exactly. All right. Here's how this was scored. 5 points. 1 point for sets up ratio test. You could also have set up the root test. But this setup is worth a point. Okay, the next point was given for computes the limit of the ratio test. So right here, this was worth a point right here. Okay. Next point was the radius of convergence. You don't need to say what the radius of convergence is, but they need to see it. And the radius of convergence is shown right here. That's for that. That will get you that point. Another way you can show it is right here. One of those two ways needs to be shown. The next point was considers both endpoints. So when we considered this, we got that point. Even if our analysis was wrong, considering the endpoints got you those points. And then the last point was for the analysis of the endpoints and your answer, your interval of convergence. Okay? So, common mistakes I see when I'm grading these tests. Common mistakes. First of all, people don't write the limit. If you don't write the limit, you are not using the ratio test. So it doesn't matter what you do, you're not using the ratio test. You have to write a limit. Another common mistake I see is kids not simplifying this correctly. Getting here, usually once you get here, you do okay. The next mistake I see is you know to examine the endpoints, kids don't put the sigma. If you don't put the sigma here, you're not examining a series. You're just examining an expression with ends in it. Okay? Put the sigma, that makes it a series. Then you can say diverging or converging. If you don't write the sigma and you write diverging or converging, that means nothing. Only a series can converge or diverge. So make sure that you write the sigma down. Another mistake I see is putting this x value in for the ends. It's an x value, so you put it in place of x, not your ends. Big points, these are points that you can get. So make sure you get everything. Part C, let P sub 4 be the fourth degree Taylor polynomial for f about x equals 0. Use the alternating series error bound to find an upper bound for this expression. Okay, so they tell you which test to use. This is not Lagrange. This is just your alternating series error bound. Okay, so the alternating series error bound is only good if our series is alternating in sign and decreasing in magnitude to 0. So I need to write what P sub 4 is here. P sub 4 at 2 will be the first, well, up to the fourth degree term here with 2's in place of the x's. So I'm going to write 2 squared over 3 minus 2 cubed over 3 squared times 2 plus 2 to the fourth over 3 cubed times 3. All I did was replace x with 2 there. Okay? So this is alternating in sign So I actually will say that the Taylor series is alternating in sign and decreasing in magnitude, in magnitude to 0. That's our condition to use the alternating series error bound. So that's what is decreasing in sign, alternating in sign, decreasing in magnitude to 0. So the error in this, they wrote it like, usually I write the f first and then the polynomial, but it doesn't matter because of the absolute values, is less than or equal to the absolute value of the first omitted term in your approximation. What was the first omitted term in our approximation? It was negative 2 to the 5th over 3 to the 4th times 4. I just go to my next term in the pattern. The first omitted term, right? And so that is our upper bound right there. That's all we need to say. So our upper bound is 2 to the 5th over 3 to the 4th times 4. This was worth 2 points. 1 point for uses 5th degree term, which we did. We used the 5th degree term, and 1 point for the answer. Okay? Remember always that your error will have no x's in it. All right? It will have no x's and no n's. All numbers. All right? Okay. Next up, let's see. What did I want to do next? The problem from 2017. Let's take a look at that. It's a good one to do together. Again, number 6, shocking, no calculator. We're given this information. So what did they give us? They gave us f of 0, f prime of 0, and then they gave us a way to find all additional derivatives. So all the other derivatives. It says here that a function f has derivatives for all orders for this, so they're giving us an interval there. The derivatives of f satisfy the conditions above, and the Maclaurin series converges to f for this. So they've given us our radius of convergence and our interval of convergence. Show that the first 4 non-zero terms are this. So they tell us what the first 4 non-zero terms are, but they say to show it. So in essence, we are going to find the first 4 non-zero terms, but we already know what they are. Okay? So how do you find the first 4 non-zero terms? Well, we start with f of x. Right? I don't know of an equation for f of x, but we always go off to the side and find f of 0. And this time they gave it to us as 0. Then the next thing we do is we find f prime of x, right? And then we put 0 in place of x. They gave us that. Now we're going to find the second derivative, right? Well, they're giving us a way to do that. So the second derivative, I shouldn't say f squared, the second derivative at 0 will be, the second derivative of 0 will occur when n is 1, correct? So I'm going to be putting 1 in for n here. So this will be negative 1 times f prime of 0, which was 1. So negative 1 times 1 is negative 1. Now I go to the third derivative at 0. The third derivative is when n is 2. So I'll have negative 2 times f, the second derivative of f at 0. The second derivative of f at 0, which was negative 1. So that will be positive 2. We need to do the fourth derivative because we want the first 4 non-zero terms, and so far we only have 3 non-zero. We will only have 3 non-zero terms. So the fourth derivative will occur when n here is 3. So that will be negative 3 times the third derivative of f at 0, which was 2. So that will be a negative 6, right? So now I can write the first 4 non-zero terms. So the first 4 non-zero terms will be, we're starting at that 0, then we go to the first degree term. I might even write down that 0 for our first, because I'm going to have to clean this up in a second. So I have my first derivative over 1 factorial times x minus 0 to the first power. Then I go to the second derivative. The second derivative over 2 factorial x minus 0 squared. And then the third derivative over 3 factorial times x minus 0 cubed. And then lastly, the fourth derivative over 4 factorial times x minus 0 to the fourth. Right? And then we would keep on going, but those will be the first 4 non-zero terms. And so the first 4 non-zero terms will be x minus x squared over 2, and I'm writing it in the form where they told me to write it, plus x cubed over 3, because 3 factorial is 3 times 2, the 2's cancel, minus 4 factorial is 24, so that will be x to the fourth over 4. So I got there. This was worth 4 points. Is that what 4? No, I'm on 20. I was reading off of 2016. This was worth 3 points. 1 point was for f double prime of 0, f triple prime of 0, and the fourth derivative at 0. That was 1 point. The next point was for verifying the terms. And then the last point was for the general term, which we did not do. We did not do the general term because I didn't read the question accurately. We do need the general term here. So let's write the general term here. We're going to need a negative 1 to the n because we're alternating in sign. Let me write the general term up here. Negative 1 to the n, and then x to the n over n, right? And I would put that right here, plus dot, dot, dot at the end, okay? All right, so let's make sure that we read our directions carefully. Okie doke. So that was worth 3 points. And again, you will have plenty of space. You will not have to squeeze in like I just did. You'll have plenty of space. Part B, determine whether the Maclaurin series in Part A converges absolutely, conditionally, or diverges at x equals 1. Okay, well at x equals 1, I will have the sum of this when x is 1. So negative 1 to the n, 1 to the n over n, which is the sum negative 1 to the n over n. We know that that's our converging alternating series. And we also know that this converges conditionally because if we get rid of the alternating, that would be our diverging harmonic series, or you can say diverging p-series. So therefore, when x is 1, the series converges conditionally. That was worth 2 points for converges conditionally with a reason. So you have to give the reason. You have to say the reason. The non-alternating diverges, the alternating converges, so our series converges conditionally. Part C, write the first four non-zero terms and the general term for this Maclaurin series for g of x, which is this integral. So I'm going to write that. G of x is this integral. Which is approximately equal to, so I'm going to replace f with my series for f, which we found in part A. And since they told me to put t's in for x, I'm going to put t's in for x, if at all possible. This is something that I struggle with because I get to going too fast. Since they want the general term, I'm going to write the general term here and just manipulate my general term. Oops, I almost put an x over n plus dot 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 dt. Okay, so this is going to be t squared over 2 minus raise your power by 1, divide by your new power. Raise your power by 1, divide by your new power, keep on going. And even here, we can raise the power by 1, divide by our new power. And we are evaluating that from 0 to x. Replace every t with x. And then when you put 0 in for t, you're going to get just 0 for that part. So that is the first four non-zero and the general term for the Maclaurin series for g. This was worth 3 points. 1 point for the first, actually it just says 2 terms. So if you got any 2 terms correct, you got you got that point. 1 point for the remaining terms, and 1 point for the general term. Okay? All right, part D. Let P sub n of 1/2 represent the nth degree Taylor polynomial for g about x equals 0, evaluated at x equals 1/2. So we're replacing x with a half in our Taylor polynomial for g here. Okay? Use the alternating series error bound to show that this is less than 1 over 500. Okay? So they did not ask us to find this P sub n at 1/2. They didn't ask us to find that. All they asked us to do was to show that this was true. So I'm going to write that out. So P sub 4 at 1/2 minus G at 1/2 will be less than or equal to, I'm using the alternating series error bound. Okay? Now, I'm going to write this, but then I'm going to have to give the conditions for it so that would allow me to write this. So I know that this is less than or equal to the absolute value of the first omitted term. If I used the 4th degree term in my approximation, then the first omitted term would be the 5th degree term. The 5th degree term is right here. It is not the 5th term, it's the 5th degree term. Okay? Because the 4th degree Taylor polynomial goes up to the 4th degree term. So the first omitted term will be the 5th degree term. So that will be negative x to the 5th over 5 times 4, where x is 1/2. So 1/2 to the 5th over 5 times 4. Since G, since P at 1/2, the Taylor polynomial for 1/2, actually I would say the terms of the Maclaurin series for g of x are alternating in sign and decreasing in magnitude to 0. Remember that was our phrase that we used whenever we were using the alternating series error bound. The terms are alternating in sign and decreasing in magnitude to 0. Now they want to show that this is less than 1 over 500, and the easiest way to do that is just to come in here and write that is less than 1 over 500. That's the easiest way. Now, if you can't stand it and you have to convince yourself that that is less than 1 over 500, then come off to the side and do it, okay? So if you did, I would have 1 over 2 to the 5th times 5 times 4. 2 to the 5th is 32. 5 times 4 is 20. 32 times 20 is 640, which is less than 1 over 500. I don't want AP to see that, so I just cross it out. Don't spend time erasing it. That was worth just 1 point. 1 point for the error bound. Just a point. Just a point. That seems like not enough. Okay, the next one I really want to do with you is the problem from 2015. So let's go take a look at 2015. I don't know if I said this to you or not, but in 2018, I know I didn't. I don't remember saying this to you. I know I didn't. Back in 2018, the first one we did, the global average was just a 2.7. That's really, really not very many. 2.7. The KHS average was a 3.1. Still pretty low. Okay. Now I'm going to do the problem from 2015 with you, and I'm leaving you the problem from 2019. It's the very last one in your pack. Well, it's the last one in this packet. I don't know where it is, where it will be every year, but right now it's. But anyway, the one from 2019 had a global average of 3.8 and a KHS average of 4.2. So when you're working this problem, see how you compare to other students, okay? Keeping in mind that if you can maintain the average, the global average, that's on track to get a 4. If you're right at average, that you're on track to get a 4 on the AP exam, okay? If you do a little bit better, then you're on track to get a 5. So keep that in mind as you're working that problem. See how you do. All right, 2015. The Maclaurin series for a function f is given by this series, this power series, okay? And converges to f of x for the absolute value of x is less than r, where r is the radius of convergence. That makes sense. Use the ratio test to find r. Well, it was very nice of them to tell us what test to use. Since they told us what test to use, though, we need to use that test. Do not go use the root test because you're not doing what they told you to do. Usually, if they just ask us for the interval of convergence, if you choose to use the root test, you may. But if they tell you what test to use, absolutely don't go and do anything goofy. So I'm going to have this -3 to the n minus 1, right? -3 to the n minus 1. Now, since we're taking the absolute value, and we could rewrite this as -1 to the n minus 1 times 3 to the n minus 1, right? Since we're taking the absolute value, I'm not going to write that negative. I'm just going to make this 3 to the, and I'm replacing n with n plus 1, so that will just be an n. x to the n plus 1 divided by n plus 1 times the reciprocal of the nth term, so that will be an n on top, 3 to the n minus 1 times x to the n on the bottom. Okay, time to simplify. The 3's reduce, leaving a 3 on top, has a 1 higher exponent. The x's reduce, leaving an x on top, because that exponent is 1 higher than the exponent on the bottom. The n's do not reduce. We write them down and let the limit take care of them. As n goes to infinity, n plus 1 goes to 1. So we are left with the absolute value of 3 times the absolute value of x, and we force that to be less than 1 because we want it to converge. Divide both sides by 3, so r is 1/3. This was worth 3 points. 1 point for sets up ratio test, 1 point for computes the limit of the ratio, and 1 point for determines the radius of convergence. Okay, part B. Write the first 4 terms write the first 4 non-zero terms of the Maclaurin series for f prime, the derivative of f, and then express f prime as a rational function for the absolute value x less than r. Let's see where we go here. So first of all, we're finding f prime. So f prime will be, I'm taking the derivative here, right? So the derivative of x is 1. The derivative of -3/2 x squared, power rule, so multiply by 2, the 2's will cancel. I'll have -3x to the first. Here we'll have positive 9x squared. Do we know what the next term is going to be here? This was a problem. The reason we may not be able to tell right off is because they simplified as they went. If they hadn't simplified, it would be easier for us to tell. If you're in doubt what the next term is, then we can use this, where n would be, gosh, this is blurry, where n would be 5, right? Because 5 minus 1 is 4. Actually, I'm sorry, n would be 4, because we'll have x to the n. N would be 4, so we would have -3 cubed, which would be -27. But then we would be dividing by, well, we'd have x to the 4th, and when we multiply that 4 down, it would cancel out with this 4, so that would be an x. Did you see that it would be a -27x to the 3rd here? Sorry, x cubed. That's hard to see. That's a 3. Okay. This looks like a geometric series, and it is a geometric series. The general term here, the n's would cancel, and we'd just have -3 to some exponent times x to an exponent. That's, anyway. So those are the first 4 non-zero terms. Okay. Now we want to express f prime as a rational function for our on our radius of convergence. So this is geometric. So this is a geometric series with the common ratio being a negative, I know it's negative because we're alternating signs, 3x, because each time we're multiplying by a negative 3x. Okay? And the first term is 1, so the function must be 1 over 1 minus a negative 3x. Must be. So this is f prime as a rational function if x is less than 1/3. Okay? This was worth 3 points. 2 points for the first 4 non-zero terms. 1 point for the rational function. Okay. Write the first 4 non-zero terms for the Maclaurin series for e to the x. Well, this was our memorized. 1, it's all positive, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus ... Those are the first 4 non-zero terms. Okay? Use the Maclaurin series for e to the x to write the third degree Taylor polynomial for g to the x is equal to e to the x times f of x about x equals 0. So g of x is equal to e to the x times f of x, which will be our series for e to the x times our series for f of x. F of x? Yes. I'll make sure I didn't forget to write a prime there. I'm copying down our series for f of x. So all I did right now is just write the 2 series in here, right? Now, we want to write the third degree Taylor polynomial. Right now, it is not the third degree Taylor polynomial because we have a product of 2 infinite series. That's not a third degree Taylor polynomial. Even if we get rid of the ... dots here, that is not a third degree, that's not a Taylor polynomial at all. We have to actually multiply out this. Okay? So let's start. I'm going to start with the 1 and I'm going to distribute it. Now, do I need to distribute it throughout the infinite series? No, because I'm going to stop when I get to the third degree term. So 1 times x is x. 1 times negative 3 halves x squared, and then 1 times positive 3x cubed. Right? Now I'm going to go to the next term. It's a positive x. So x times x is x squared. X times negative 3 halves x cubed, and then x times the next term will be positive 3x to the 4th, which I don't want to write because I've gone higher than the third degree term. So I'm not going to write that one. Go to the next piece. Multiply this by the terms here. So we're going to have x times this, so that will be a positive x cubed over 2 factorial. Now, do I want to go further? No, because I've already reached my that would be 4th degree, and I don't want to go to the 4th degree. Do I need to go over here? Do I need to multiply this? No, because that would be a 4th degree term. So I'm done multiplying. I have my pieces, but I need this to look like a Taylor polynomial. Right now it does not look like a third degree Taylor polynomial. I need to collect my like terms. So I have only one x to the first, so I'm just going to write that by itself. Now I'm going to go find all of my x squareds. I have an x squared here and an x squared here. I'm taking out my x squared and I'm going to put it in the back. So I'm going to write this as plus something x squared. I'm going to have negative 3/2 plus 1. Now that's safe stop. I don't have to add that together. That's just safe stop. And now I'm going to do the same thing for my x cubes. I'm going to write my x cubed out and back. And I'm going to write all my coefficients inside the parentheses. So positive 3 minus 3/2 plus 1 over 2 factorial, which is 1/2. Now it looks like a third degree polynomial. So that's my safe stop. So this was worth 3 points. 1 point for the first 4 non-zero terms for the Maclaurin for e to the x. 2 points for the Taylor polynomial, the third degree Taylor polynomial. Okay? So an interesting little problem, don't you think? I really like that last part. We never did anything like that in our unit. We certainly could have, but we didn't. Okay? Alrighty. So again, when you're doing the problem from 2019, see if you can how you do compared to the average student that year. All right. Have fun doing these problems. All right.